Today's seminar speaker is Dr. Mogeng Li, and welcome. Morgan received her PhD from the University of Melbourne, where she studied turbulent flows over rough walls, and she worked in collaboration with the Melbourne Fluids Group. After that, she moved to Twente, where she is now, and she's a postdoctoral fellow. She's working with the Fluids Group at the University of Twente, and where she's studying sprites and bubbles. And today she's going to give us an overview of the topics. Morgan, the floor is yours.
Okay, thank you, Davide, for the introduction. So today the talk, okay, I should have said that. Thank you for inviting me as well. The talk today is going to be about two topics which are linked eventually to turbulence. The first part of the talk is based on my PhD project. It's going to be, I'll talk about high Reynolds number turbulent boundary layers and how rainfall is going to affect the flow. And in the second part, I'll be presenting some of the recent works I'm doing now in the University of Twente. We are looking at the evaporation of droplets in the presence of turbulence. So if you have any questions, please feel free to stop me during the talk. All right, let's begin with the first part. The motivation of this study is that we have quite a lot of knowledge about how roughness modifies the flow, how it influences the drag and flow structures, etc. And but in reality, we often see certain scenarios that we have a change in roughness. So the height of roughness is not uniform in the space anymore. We have this kind of a change of, we have a patch of very rough surface, and adjacent to it, we have some smooth surface. If there's a flow over it, we want to know what's the response of the flow to such a change. A more practical application is if you want to understand, for example, the local climate of a coastal city, then we really need to take into consideration how the flow adapts to such a smooth to rough change. And one final example is this picture taken from a ship in Indonesia. This is an example of biofouling. Biofouling is some marine creatures like barnacles or other mussels, I believe. They attach themselves to the objects we submerge underwater, for example, ships. And they settle close to each other and form colonies. So we have a big patch of roughness here. This roughness will increase the fuel consumption. It will lead to drag penalty. If you want to have an accurate estimate of how much additional fuel consumption this leads to, then we again need to understand the response of flow to heterogeneity in roughness. We are going to take this one as an example and assume the flow goes from left to right of the space. And we can simplify it as a two-dimensional flow field as shown by this cartoon here. We'll be using Z for the wall normal direction, the Melbourne convention, and X for the streamwise direction. The rough wall is in the upstream, covering up to the point of X0, and the downstream is left as a smooth wall. I'll be using X hat to refer to the distance on the smooth surface, also call this the fetch. When a flow sees such a change in the surface roughness, it will first respond to it at the wall, and then the region of modified flow gradually expands and propagates to the interior of the fluid. This region where the flow is modified by the new surface condition is called the interlayer, with the thickness denoted by delta I. And above that, in this layer, the flow carries the upstream rough wall characteristics, which can be described by the friction velocity, Ks, the equivalent sandgrain roughness, and delta naught, which is the boundary layer thickness at this point. The ultimate goal of our study here is that we want to build an analytical model so we can take the upstream conditions, feed it into the model, and predict what's going to happen in the downstream. So to put it in a mathematical language, we want to solve for the unknowns that characterizes the flow downstream, which are U tau, the local friction velocity on the smooth wall, and delta I, which is the thickness of the internal boundary layer. Both of them are functions of X hat. We can look a bit closer to the parameter space we have. These three quantities can be grouped into two independent non-dimensional parameters to fully describe the upstream. We have Ks plus and Re tau naught. And if we want to study these two factors independently, we design the experiments like this. First, we hold Ks plus constant and increase Re tau naught from 7,000 to 21,000 to look at the effect of Re tau naught. And then we take another cut in the parameter space where we hold Re tau naught constant and increase Ks plus. We did all of these experiments in the high Reynolds number boundary layer wind tunnel in the University of Melbourne. This tunnel has a working section of 27 meters long, which is great for studying such high Reynolds number cases. We cover the upstream part of the tunnel with a piece of sandpaper, and the downstream is left as the original aluminum surface. These are the cases I conducted. I achieved the range of Re tau naught and Ks plus by manipulating the length of the sandpaper and the free stream velocity. These are all the cases, and these are the symbols I assigned to each case, but I'm not going to go into, I'm not going to bother you with the numbers. So I'll just show you the measurement techniques we used. First is the hot wire anemometry. We performed wall normal hot wire profiles at a number of streamwise locations marked by these symbols here. We have more points closer to the transition and larger spacing towards the end. And at each hot wire measurement location, we also did oil film interferometry. This is a method to measure the wall shear stress directly without any assumption of the how the velocity profile looks like. And there is another set of experiments which were done in a smaller wind tunnel. The working section is less than 7 meters long. In this set of experiments, the Reynolds number Re tau naught is 4,000. It's a bit lower than what we had in the big tunnel. And the focus was on the effect of step height when associated with this rough to smooth transition. So we can have smooth wall below the roughness valley or above it, or comes in between. But in the presentation today, I will not discuss this part of the result, but only using some of the high magnification particle tracking velocimetry data from this set of the results. The highlight of this measurement is that we have really zoomed in field of view. The height of the field of view, as you can see here, is only 3 centimeters. So that means everything is so magnified, and we have a lot of data points even within the viscous sublayer. So we can fully resolve the velocity in there. I'm going to structure the first part of my talk with the outline listed here. I'll first show you what we have learned from the experiments. And then with this knowledge, we are going to attempt at building an analytical model to predict the flow. So first, I'll talk about wall shear stress and mean velocity profile. Here I'm showing the skin friction coefficient plotted against the fetch x hat, and I'm normalizing that. I'm dividing that by the smooth wall CF, which is the value we expected to have when the flow is fully recovered. So on the rough wall, it is expected that this ratio is more than 1 because rough wall has a higher skin friction velocity. And as soon as it goes through the rough to smooth transition, the CF undershoots and gradually increases and recovers to the smooth wall state. This is the behavior we generally agree in the literature. But if we collect the data and overlay them on top of each other, they generally follow the trend, but there's quite a bit of scatter in here. There are several possible factors contributing to such a big scatter, for example, Reynolds number, roughness, geometry, etc. But what I want to highlight here is the last one, the method we use to obtain CF. By that, I can color code these data sets based on the region which were assumed to be in equilibrium with the new surface condition to obtain CF. If we assume the viscous sublayer, the mean velocity in the viscous sublayer to be fully recovered, it will be green. And if it is buffer region, it's gray. And the black one is for the log region. And the most representative method in this category is the closure chart method or log-log fit. And we can see some kind of separation after we color code the data. It seems that all the green symbols are concentrated on top of this graph. So this is very curious. It seems that using different methods will give us different results. To understand the reason behind this, I'm going to use my high magnification PTV dataset and compare that with the smooth wall boundary layer profile from a DNS simulation. Because I have many data points in the viscous sublayer, I can use the gradient of the velocity profile to estimate CF directly, to estimate util, well, essentially CF. And this is how it looks like when I overlay my PTV velocity on top of the smooth wall reference, as dictated by the method I used to calculate util. This part in the viscous sublayer, the two profiles collapse on each other. But in the buffer region, there is quite a bit of mismatch. And I keep adding a few more downstream locations to show the general trend. Again, we can see that all of them, there is a mismatch in the buffer region. So this means that if we force the mean velocity in the buffer region to collapse on a reference smooth wall profile, this is not going to give me the right util. You may say this is obvious with the PTV data because we can clearly see that the data points are not looking all right here. But what if in most data sets, when we do hot wire measurements, it is very rare that we can go closer than 10 wall units to the wall at such a Reynolds number. So we can't really see the problem, and this is very dangerous. To further drive to further make the point, I'm going to show you the skin friction coefficient calculated with these two methods. The green triangle is from viscous sublayer fit, and the blue dots are from the buffer region fit. And you can clearly see that the buffer region fit is much lower than the PTV data. And finally, I'm plotting my oil film interferometry measurement as well, which is a direct measurement without relying on the mean velocity here. And that has a much better agreement with the viscous sublayer fit. So the takeaway message is that if we want to have an accurate measurement of the wall shear stress right after the rough to smooth change, we really have to get the mean velocity information in the viscous sublayer. Above that, the flow has not recovered to the smooth wall state yet, so we cannot do a fit like that. All right, now let's move on to the turbulence statistics. And here is a streamwise turbulence intensity of a smooth wall reference profile plotted in the viscous scaling. Here is the inner peak at z plus equals to 15. And I'm going to put my rough to smooth data on that as well. What we see here is the inner peak, well, it is there, but it's a bit higher than the smooth wall reference. And what's more notable is that we have a very strong outer peak. This is the result of the very energetic rough wall structure got convected downstream together with the flow. So we have a blob of energy here. The location of this outer peak, the so-called outer peak, coincides with the internal layer thickness, delta I. I'm going to show you a bunch of other streamwise locations. So we can see that as the fetch increases, the magnitude of this peak decreases. That means the structures are losing their energy and the internal layer is growing at the same time. The location of this peak is moving outward. Another thing to note is there is a more gradual change at the location of the inner peak. as the fetch increases, we see a decrease in the magnitude here as well. This is puzzling. And to understand what's happening here, we can take a look at the pre-multiplied energy spectrum to see how the energy distributes at different wavelengths. This is the pre-multiplied spectrum at Z plus equals to 15. And again, color corresponds to different streamwise locations. And the thick black line is a smooth wall reference. I'm plotting it against the time period, but essentially you can think about the left half of the figure is a smaller wavelength or small scale structures, and the right end of the figure is large scale structures. The small scale end, well, everything collapsed over there, but at the large scale, we can see some excess energy. If you look at the yellow line here, and this blob of excess energy decreases as the fetch goes up, as the fetch increases. A bigger picture is if we do the same thing at all wall normal locations. So we can show that in a color contour map like this. The color is the rough to smooth change, and the solid black line is the smooth wall reference. I'm going to subtract the smooth wall reference from the colored contour to show you the difference. We can see the results here. This big blob of energy, that's the remaining rough wall structures, they move outward as the internal boundary layer grows. By the way, this dashed line shows the location of delta I. But at the same time, if you look at this figure here, delta I is already at 1,000 wall unit here, but it still manages to leave a footprint very close to the wall, like at Z plus equals to 10 or 15. So these are actually the so-called large-scale footprints, which are also observed in smooth wall boundary layer profiles. But here it's based on kind of a different, the energy difference point of view. These are the large-scale structures coming down directly from these rough wall structures over here. Another point to note is if we now focus on the near wall small scales, which are boxed by these pink lines, we can see there is almost negligible difference in energy. So that means the small scale structures recovers very quickly in the near wall region. They recover much quicker than the mean velocity profile. And this inspires us that we might have an alternative way to find U-tau if we only have half-wire data. If we don't have any mean velocity in the viscous sublayer, we can still recover U-tau from the energy spectrum. We can take this case as an example, and I'll show you the process. Let's just consider for a minute that we don't have the oil film result anymore. So what we can do here is we'll keep adjusting U-tau and Z0, which is the wall positioning correction for hot wire measurements. We keep adjusting them to minimize the difference in this pink box. And when the difference is minimized, we say this is our optimum U-tau. And now we can define an error to see how well this method performs. We'll use the oil film CF as the reference and calculate the relative error with this equation here. And the results are shown here. The solid symbols are from spectrum fit, and the open symbols are from the buffer region fit. Now we can clearly see which one is the winner. The spectrum fit data points are all within about 5% difference with the oil film data. All right, so let's now move on to the modeling part. This part of the work was done in collaboration with Professor Del Polin from Caltech. First, I would like to give you a recap of a classical model on this topic, and we go from there. This model was published by Eilert in 1958. He considered a deep surface layer where the boundary layer thickness is infinity, or it's so big that it's not really relevant in this process we are interested in. So delta naught is removed from the upstream condition, and he also modeled the velocity profile in the downstream with a piecewise log law model with two different slopes. Within the inner layer, he assumes that it has a slope of the local smooth wall utile, and above the inner layer, he assumed that the slope has a rough wall utile knot. And these two log laws intersect at delta I. To sum it up, in this equation, we have two unknowns, the utile on the smooth surface and delta I. And we need two equations to close the system. The first equation is the continuous velocity profile, or these two log laws intersecting at delta I. There shouldn't be any jump at this point. It's also, you can call it the matching condition. And the second equation is he looked at the momentum equation in the inner layer. Since we have experimental data, we can check the assumptions in this model and see how we can adapt that to our problem where we have a finite thickness for the of the outer layer. So here I'm showing the mean velocity profile again, and I'm going to show the modeled mean velocity profile by Elit at matched condition. For the rough wall part, the log region agrees okay, but obviously the weak region is missing, and a more significant problem is actually in the internal boundary layer. And the reason is that he assumed the mean velocity in this part is already fully recovered to the smooth wall state, and that's actually not the case. As many studies have shown, the mean velocity profile takes a very long time to reach a fully recovered stage in the internal layer, and we also discussed that when we showed our wall shear stress results. So what can we do to improve this model? We can go back to the physics. We know that very close to the wall, like within the viscous sublayer, the flow should be in equilibrium with the local smooth wall condition. So we can model that. We can approximate that with the smooth wall profile as shown by the blue line here. And above delta I, it can be described by a rough wall profile, which is the red line. Now the question is, what's going to happen in between? Well, here we are adopting this blending model from Chamorro and Porteago in their 2009 paper. They proposed a blending model, a blending function E, which decreases monotonically from 1 at the wall to 0 at the interface or at the location of delta I. So if we, for example, plug E equals to 1 into this equation, we can see that it recovers to the smooth wall profile at the wall. And if you plug E equals to 0 in it, it recovers to the rough wall. We can rearrange the terms in this equation so we can evaluate E from our experimental data. And this is the result at a number of different streamwise locations. Indeed, E is decreasing from 1 to 0. In the original paper of Chamorro and Porteago, they used a linear function, a log linear function to model this blending function E. But that doesn't agree very well with what we observed experimentally. So instead, we propose to use this error function with two fitting parameters to describe the blending process. And with this, we can go back to look at our mean velocity profile. The blended velocity is shown by this thick multicolored line, and that has a good agreement with the experimental data. All right, on top of this blending velocity, I we propose another two refinement or modification to the original ALIS model. The first one is the shear stress condition. To understand this, we need to look at the momentum equation he used. He considered control volume of which is bounded by the interface, by the upper bound of the interlayer and the wall. So there are two shear stresses going into this momentum equation. There is very little ambiguity of what the shear stress should be at the wall. It's just local wall shear stress. That's easy. But on the top surface, he simply used the wall shear stress of the upstream rough surface. This was okay in his case because he was looking at the deep surface layer. So he assumed that the interlayer is always within the constant stress layer. So that's fine. But for us, if we look at how the shear stress varies in the wall normal direction, we can see that the constant stress layer is only a fraction of the total boundary layer thickness. That means if our delta I exceeds this region, if we have a delta I of, let's say, 40% of the total boundary layer thickness, what ALIS used was no longer good for us anymore. So what we did in the end is we fit a curve to these data points, and we use this line, and we use this one instead of a constant shear stress in the equation. The next refinement is we need to consider the growth of outer layer. Again, this is a new problem appeared after we started to consider finite boundary layer thickness. So that means we have to introduce two additional variables, two additional unknowns, the total layer thickness, delta C, and the corresponding friction velocity of the upstream surface, utah naught. And we'll need to add two more equations to close the system. Okay, without going into too much details, I'm going to show you one final plot on this topic to show you how the new refined model compares with the original ALIS model. The black line is the ALIS prediction, and the colored symbols are my experimental data. The refined model works, has a better agreement with the experiments. So that concludes the first part of my talk. Perhaps I should stop for questions if there's any, or if you want, I can continue with the second topic.
I think you can, well, let's see if there's any question. You can also ask questions at the end about the first topic, I think.
Okay, yeah, because I'm in full screen and I can't see anything happening in Teams now.
yeah, but we're still here. We didn't,
okay.
We didn't disappear, okay.
Okay, all right, so I'll continue and we can have a discussion in the end. Okay, the second part is about evaporation of droplets in quiescent and turbulent environment. The motivation of this study, well, I don't have to say too much about it. It's inspired by the current situation we are living in. With this pandemic going on, we realized that the evaporation of respiratory droplets is very important in the transmission of disease. So what we have done so far is that the evaporation process is very sensitive to ambient conditions. For example, the relative humidity of the environment or the temperature. But what's left to be answered is the effect of ambient turbulence. And to answer this question, we built a device called the dodecahedron. It's essentially a dodecahedron-shaped chamber that we use to generate a homogeneous isotropic turbulence field at the center. It is a closed system, and we can also monitor and regulate the temperature and relative humidity inside it. For the droplets, we collaborate with this local company called MaxPre. They produce a type of nozzles that can generate very fine liquid droplets. The one we use here can generate droplets with initial diameter around 10 micrometers. And for the working fluid, we choose to use Novak 7000 engineering fluid rather than water because it has a very high vapor pressure at room temperature. What it means is that it will evaporate very quickly, And the benefit of that is when we look at the damp Koehler number, which is the ratio between turbulence timescale and vaporization timescale, we'll see that with water, this number is very small. That means the turbulence timescale is very short compared to the vaporization timescale. So when the droplets is simply moved around by turbulence without much change in size, and that's not very interesting to us at this stage. So that's why we decided to use this Novak engineering fluid. We measured the droplet velocity, 2 components, and the droplet diameter with this laser Doppler anemometry and phase Doppler anemometry system. The measurement volume is fixed at the center of the chamber. First, I'm showing the time series of droplet sizes. These data were taken in the quiescent case, and I'm only showing the first 0.1 second of the data, but the actual sampling time was 30 seconds. We took measurement at a number of different distances from the nozzle along the center line. We start from very close to the nozzle at 20 millimeters and goes all the way to 60 millimeters away from the nozzle. Overall, the droplet size fluctuates between 0 and 10 micrometers. And as we go further and further away from the nozzle, the number of droplets captured decreases a lot. What if we introduce turbulence? Well, judging from this figure, the size, at least the range of the size doesn't change that much, but the number of droplets captured decreased a lot. For example, if we look at this one, at this location, x equals to 40 millimeters, we see some big patches of time intervals where there were no droplets captured at all. We can quantify, we can look at the size distribution more quantitatively by looking at the particle size distribution in this graph here. Again, the color yellow means far away from the nozzle and blue means close to the nozzle. And this is the quiescent case. What's really interesting here is that we see the distribution starts with the initial size around 6 or 7 micrometers. This is expected. But as we move away from the nozzle, we see the rise of a second peak, which is centered about 2 micrometers. This is very small, and this is really puzzling because a Novak droplet of this size would evaporate in no time. It will be like in, I think I did a calculation before, it takes only 0.02 milliseconds for it to fully evaporate. So this is very puzzling. But just before I go for the explanation of this, I'll show you the turbulence case. Oops, sorry, I forgot the arrows. I'll show you the turbulence case. It confirms what we saw in the quiescent case as well. So this weird peak, it is still here. We conjecture that this peak is likely to be droplets formed by the water condensation on a fast evaporating Novak droplet. What I mean is when the Novak droplet evaporates very quickly, it absorbs a lot of heat from the ambient environment. So the surface temperature becomes very cold. And the moisture in the air will condense on a cold surface. This is like in our day-to-day life. If we leave a glass of cold drinks outside, we can see this tiny water droplet condensation formed on the glass. We can model this evaporation condensation process for, using the framework developed by Murray et al. There are a few assumptions to be made. We assume that the droplet is stationary and the evaporation and condensation rate is limited by the vapor diffusion process. So we have 2 mass transfer equations, one for the Novak and one for the water component. And these 2 equations are linked together by a heat transfer equation. After solving the system, you can see for a droplet with the initial diameter of 10 micrometers, it will evaporate in 2 milliseconds and will be left with a water droplet with a diameter of 2 micrometers. We can apply these results to our experimental data. We take this measurement, which is closest to the nozzle, as the initial condition and feed that into the model. So the residue water droplet size predicted by the model is shown by the black line here. The location of the peak agrees well with what we observed. We can further define a threshold of 3 micrometers, and we say everything below that are fully evaporated water droplets. And what we can do here is we'll use them as markers and see what's the ratio between the number of fully evaporated droplets over the entire population of droplets we captured at that point. So we are going to look at the percentage of fully evaporated droplets along the center line. In the quiescent case here, it increases from about 10% to 90%. And we also did a profile in the radial direction. The percentage increases from 40% to 100% in just 10 millimeters. Now, if we overlay our turbulent case on top of this, we can see there is actually very little difference between the two. So it's a bit disappointing, but we think the reason behind it is there is probably lack of interaction between the turbulent jet and the ambient turbulence because they have very different timescales. So the next step in our work is to bring these two timescales closer to each other. So hopefully we can get some more interesting physics. And that's all from me today. Thank you so much for your attention. And I'm happy to answer any questions.